All right, guys, so do you remember what those things stand for? So what is 0.777? That is the same as 7 over 10 plus 7 over 10 squared plus 7 over 10 cubed, and so on and so forth, right? Let's call the entire thing, let's call it S. This is my S. Now, if this is my S, this in parentheses also looks like an S, except I need to change a little bit. What I change is I factor something out. You agree? I factor something out, and what do I factor out? I factor 1 over 10. Factoring 1 over 10, I get 7 over 10 plus 1 over 10. Why do I factor out? Because then what's in the parentheses now becomes S. So I have that S equals to 7 over 10 plus 1 over 10S. Good? And that makes S equal to 7 over 9. I hope you see that. That's now a simple equation. 9 over 10S is equal to 7 over 10. I can cross away the 10 and divide by 9, and I get 7 over 9. For number 2, similarly, right, I will get that S equals to 4 divided by 10 plus 1 over 10S, which means 9 over 10S equals to 4 over 10, which means that S is 4 divided by 9. For number 3, the best way to, you can do it 2 over 10 plus 4 over 10 squared, but nicer to think of it as 24 over 100 plus 24 over 100 squared, and so on and so forth, right? It's much nicer to deal in base of 100. Yes? And so what's the result? The result is that I will have that S equals to 24 over 100 plus 1 over 100S, which makes S equal to 24 over 99. Now, in the morning, people ask me questions like, it's a very mysterious question, like, where do you find this information? And the answer is naturally on my website. Guys, you know that there is a website, right? I mean, I know I'm not very technological myself. You know, I have this thing that tracks my existence now, right? Like a prisoner tells Amazon where I am and what I do, right? But, you know, right? This thing on the website is a bit simpler. You just go to etkin.com and you find the information. You find my lecture notes. It's all there. Good. Now, let's see if you did not enjoy this weekend too much. I hope you enjoyed it, but not overly. Because I did mention that we should think about the monk problem. Yes? Do you remember the monk problem? The Tibetan monk problem? Let me remind you of it. Here is the Tibetan monk problem. Here is the Tibetan monk problem, the way it was phrased, guys. Do you remember it? So you have, you're making a video, and in the video on day 1, from 7 a.m. to 7 p.m., the monk climbs the mountain. It begins at the base of the mountain, ends at the very top of the mountain. Yes? You with me, guys? And on day 2, the monk starts from the top of the mountain and descends and arrives at his monastery at 7 p.m. So both videos run from 7 a.m. to 7 p.m. The problem from Thursday night. Exactly. So you see, again, mathematics is not a recipe on how to make a cake. It's not McDonald's. It's not Chipotle where you do the same mixture all the time. What you do is you have to have a sort of strategy, a sort of philosophy. So the question was, can you explain? And you want to do it in two ways. One of them very mathematical and the other is very intuitive. In two ways, could you explain why will it be the case that at least for one moment of time in both videos, the monk is on the same location on the mountain? Do you understand what I mean? So if you were to play those videos synchronously, there is going to be a place, a time bar, the same time bar, the same distance away from the beginning from both videos, and you will see that the monk is in the same location. Why is that true? And guys, it's nice to see many of your faces, and I, of course, would like to see many more. Okay, Elazar, you Googled and you cannot answer, but do not. So Elazar, by the way, means God helped. I hope that your God is not Google. And any ideas? Jomarl, please, Jomarl, please go ahead and speak.
Wouldn't there be a place where they'll both meet in the middle?
Well, what do you mean by the middle? Middle of what? Middle time interval or middle mountain?
Would it be both?
Okay, well, you see, Jamal, you are using a sort of symmetry that does not exist. So, for example, imagine you go to the store, right? If you walk at a constant rate, it takes you 1 minute to get to that store. It's right at the corner of your block. By the way, at the corner of your block, Alexander Block is what I'm thinking. In the morning, I always go to the pharmacy, right? Ночь, улица, фонарь, аптека. Right? At least one person understands my joke. So in the middle of your block. You see, guys, read things, it will be funny for you. So you go to that pharmacy and it takes you 1 minute to reach it. But now suddenly you were interrupted by something interesting happening. Maybe you met a friend. And then maybe you talked to that friend and it took you, let's say you were standing in one location for 50 seconds and then you started running because you wanted to be in the pharmacy within 1 minute. You understand? So your motion is not uniform. You can walk on day one entirely differently from day two. Well, so Sophia, interesting. You're suggesting probability, but this question is not about probability. And the way the question is stated, calculation is impossible. Now, let me explain to you why that's obvious, why it's obvious that they could have met. Oh, Grant, you made it. Wonderful. No, not the same in between. All you have to do, you can walk whichever way you like, but at the end of your time, you must be in a particular location. So here is the video, guys. Look at it. I made, of course, a very crude drawing, but I hope it's enough for you. Are you seeing this? So do you see what happens in the first video? You see where the monk is shaded red? At the beginning of this video, you see that you can say that in both videos, the initial moment is not going to be that moment I'm seeking, because in the initial moment in video number 1, the monk is at the bottom of the mountain. In the video number 2, the monk is on the very top of the mountain. Yes? So it's not this moment. Could it be the very last moment? Obviously not, because in the very last moment, their places have been changed, right? When the video is over, when the first video is over, the monk is at the top. When this video is over, the monk is at the bottom. Do you follow? Now, have you ever watched movies where you see the same actor is appearing twice within the same frame? Have you ever seen that? Like, let's say a guy is talking to himself on the couch, or supposedly to his twin, but it's the same person. Have you ever seen such a thing? Now, I mean, how to do that technically, it's not so problem. I mean, it's a whatever problem, but what you can do, you can interlace the videos, place one video on top of the other. Do you agree? Make the video somehow transparent, at least conceptually, it doesn't matter how you do it, right? Make the video transparent, place one on top of the other, and then what do you get, guys? If you make one video on top of the other, what do you see? You see that there is the monk here, and there is this monk who is his twin. Do you see that? I mean, imagine I overlays the videos, and as I play the videos, what happens? One monk is climbing up the mountain, and his twin is climbing down. However they do that, they must interchange places somewhere. You agree? At the moment when they interchange places is a moment when they meet. They might meet many times. In fact, there might be infinitely many moments of time when they actually say hello to each other, or there might be only one moment of time. But you understand, you have this sympathetic bias or symmetry bias that you think it will be in the middle of the mountain. But that's why in the middle. I mean, part of the mountain is harder to travel than another. You understand? You don't travel the same distance necessarily at the same amount of time. Maybe the mountain gets very steep and it takes you forever. It takes you maybe many hours to cover a small segment. Clear? Do you understand that what I just intuitively see by overlapping the videos that one moment will exist? But
Professor, so you were asking about like just one moment or like the same time? Because for example, if they meet on the like the first monk that's going up, he let's say covered 2/3 of the path, right? And the other monk covered 1/3 of the path.
yes,
It means that there will be less time for the second monk that has passed than for the first monk. So the time after the beginning of their path will be different.
Synchronously, right? I'm not sure how they work, but what I know about both videos is that at the end of first video, this monk is on the top. This twin monk from the second video is at the bottom. Look at it. However they move, they have to pass by each other. That's what I'm claiming. Do you see that? However they move, they have to pass by each other, which means in the video, I will see a moment of time when they are overlapping, when one monk and the other are in the same place. Do you see that? It's intuitive, I hope. I mean, right?
That yes.
So they must meet. So when you say they must meet somewhere in the middle, Eleazar, you have to be very careful about what you mean by the middle. They must mean somewhere. If you don't mean middle as in exactly between, then you are correct. They will meet somewhere between the top of the mountain. By the way, they might meet on the top of the mountain. Maybe the view is beautiful, and let's say the monk on day one really rushes to the top of the mountain, runs to the top of the mountain, and at 5 p.m. is already there and sitting there. And the second monk is just sitting there for a long time and then starts running down. You understand? The monk does not have to move. He can stand in one place for as long as he likes. His only requirement is to be on time at the bottom and at the top of the mountain. You understand? In the first video at 7 a.m. you must be at the bottom, and at 7 p.m. you must be at the top. That's the only requirement. And in the second video, the requirement is reversed. Clear? Now let's do it in terms of the... Yes, exactly, Sophia. There is no symmetry whatsoever in this particular problem in the way it's phrased. It's very rare that there would be. So now let's talk about how to solve it rigorously, right? In terms of the intermediate value theorem, okay? So here is the idea, guys. Here is how you can think of it mathematically. So first of all, I can, that's just my prejudice, I can change the units of time and change the units of distance. You agree that distance, I mean, 1 of something, 2 of something, I mean, you can just change it. So I'm going to make 0 to be the base of the mountain and 1 to represent the top of the mountain. In other words, 1 unit means 1 mountain high. You understand? all of you understand, guys, they use, what is an inch, right? They used to measure things using their fingers before you had standardized measure system. You understand? There is nothing special about a meter. It's just a unit of measurement agreed upon to be standard. But in the Bible, they measure things in terms of amma, or the or your what do you call it in English? Elbow, right? In terms of your elbow, you measure the distances. If you read ancient text, and others used other measurements. So we are going to say one mountain. Forearm, thank you, right? Elbow or forearm, I'm not sure what's the difference, right? So forearm, I suppose. So then what? Then we are going to normalize time. Normalize means I'm going to say 0 is 7 a.m. and 1 is 7 p.m. because I don't like 7 a.m., 7 p.m. stuff, okay? 0 and 1. So the video runs for time from 0 to 1, and 1 means from 7 a.m. to 7 p.m. And the altitude that the monk climbs is from 0 to 1, okay? And then I describe the following functions. So because the monk is not magical, f of t will represent the position of the monk in the first video. You understand what f of t is? Just labeling it. It means give me the time, and the time will be processed and made into the position of the monk. Do you see that? Can you imagine, guys? You see? It's a cartoon that plays in your mind. Now, if you understand what is f of t, let me just make a simple test. Okay, what is f of 0? There are some values known to us. What is f of 0 if you understood what is f? Yes, it's base, and give me the number, bottom of the mountain, and f of 0 is 0 precisely. Okay, so numerically, the way we communicate it, it's that f of 0 is equal to 0. F of 1 represents 7 p.m. Okay, the input represents time, the output is the elevation. F of 1 is equal to, help me, 1. Clear? Now, similarly, I create a function for the second video, and because the function is different, I call it g. That's a function that converts time to the actual position. Okay, and why it's the function? Because at any given moment of time, when you freeze the frame, you see that the monk is in one particular point in space. Okay, the monk is not in 2 positions of space or 3, but in 1 position of space. So what is g of 0, please? Exactly. And what is g of 1? Good. Amazing. Okay, so g of 1 is equal to 0, and g of 0 is equal to 1. I hope you see that. That's the only thing I know about f and g, and I know one more thing. Intuitively, the monk does not teleport, right? So that means gradual change in time produces a very gradual change in position, which means the functions f and g are continuous functions. Even though I don't have a formula for them, they are continuous based on this philosophy, yes? You see that, guys? So then I am interested in solving the equation f of t equal to g of t, because that means that at the time t, f is the elevation of monk from first video and g is the elevation in the second video, they match. And I can solve this equation by moving everything to the left. Look at it. It's always nice to solve against 0, right? That's why you are so obsessed about roots. They call it roots, finding when something equals to 0, because 0 tends to be a nice number to work around. So then what we define is k of t to be equal to f of t minus g of t, and k is a continuous function. Do you see that? K is f minus g. The difference of continuous functions is continuous by the limit laws, right? Because continuous means that take the limit, same result as plugging in the value. And then we have limit of the difference is the difference of limits. So I hope you understand it, guys. It is not a polynomial, most likely, Alexandra. It might be a polynomial, but we don't know, right? We don't know it's a polynomial or not. We have no idea what sort of function we are dealing with. There are many functions, and it's a very interesting question, what is a polynomial and what's not, okay? But right now, as far as we know, there are many types of functions. Many continuous functions. Okay, so then look at it, guys. K of 0, it's f of 0 minus g of 0. F of 0 is 0, g of 0 is 1, so it's 0 minus 1, which is minus 1. And that's below 0. And if I plug 1, I get a value above 0, which means by the intermediate value theorem that there must be a crossing where k crosses the x-axis. So there must be a point t0 that gives exactly 0. Are you following? Exactly 0. Good? And that point t0 is that one point guaranteed by the intermediate value theorem. Maybe there are more than one, but at least one exists. You understand, guys? So it's completely abstract how we solved it, okay? Do you see that? When you think mathematics, you think you solve for x or you do some algebra, whatever you call algebra is not even algebra, right? What you do is this, you have to have a concept and then you describe the concept. There is nothing that when people say it's like a language, that's exactly what they mean, is that what you're trying to do in symbols, you're trying to describe the idea that plays in your mind. All right, wonderful.
Meaning, Professor, meaning because we have a value that's below the x-axis and a value above the x-axis, and we know it's continuous, we therefore know that there's a number in between the -1 and 1, and therefore there's a point in which the monk will meet at the same time and place.
Right, right, exactly, Abraham. And of course, guys, it bothers me. I mean, I'm obsessive, of course. Maybe it doesn't bother you as much, but I right away want to go and teach you about the real numbers because you don't know real numbers, right? And in fact, they were discovered what they truly are in the 19th century. Okay, I could say if you do not understand why negative times negative is positive, then you cannot appreciate the problem of finding square root of -1 and why would such a problem be important. And I can show you that in very interesting, compelling fashion. It has to do with how many cats I have, by the way, if you're interested. In root of -1, root of -1 relates to how many cats I have. So decide if you are interested in listening to it, let me know. I am all yours. Not right now, that's for office hours, okay, guys? But you need to know, if you really want to understand things, you want to know deeply what real numbers are and why is it impossible in real numbers to find square roots of negative numbers, what is multiplication, what are all those processes about, okay? And therefore, what is the intermediate value theorem? Why does it truly work? It actually is a property of the real number line, okay? We say this theorem and we think it's intuitive, but truly it's something that you prove. It's a statement that is absolutely provable, okay? And it's not a hard proof, you just need to know a lot of concepts. You have to understand what's the idea of an object being intact. Like you see, here are two hands, but one hand is somehow one object. So mathematically, there is an idea of how to describe that. All right, anyhow, guys, so let's get going and talk about limits at infinity. We have a lot to say about those. So I don't remember if I covered everything. I definitely did talk about my wager. I still am waiting for my check in the mail. All right. By the way, I should have signed you like pretty much like this device. Like by default, you don't read the instructions when you sign in. You agree to all the conditions, right? And that means that if you didn't answer it, I expect that you deliver an envelope to me. Because not answering meaning that you did not understand it, and then, you know, there must be something for it. So here is where I hope you remember, guys, that a central idea in physics is that if a cord is massless, then the tension in this cord is uniform and no force can be stronger on each side. If you cannot pull an ideal string with different forces, that's a central idea in physics. I can show you many, many examples. I can show you a very good physics book that I have available online. Okay, they use it as advanced introduction to MIT. So that has to do very much with multiplication by 0 and infinity. 0 and infinity are related. Good. So we talk about that. We talked about the infinite sums a little bit. I believe, I'm not sure if I am lying to you guys, did I mention probability? Did we speak about probability? No, we did not. Maybe I did it with the other class, but not with you. Wonderful. So here is the next question. Let's see how clever you would be. You can solve it in several ways. So we have a rather boring game. In this game, we are going to take a fair die and we are going to throw that fair die until we get the number 1 or the number 6. You understand? The game terminates with the number 1 coming first or the number 6 coming first. Yes? Clear? Now, the question is, if you are to win when 6 comes first and to lose when 1 comes first, what's your probability of winning? And why? I'm of course not expecting that you know probability. Maybe you don't know anything about it, and that's okay for this class. But let's see if you can figure it out. Okay, Jasprit, interesting. Tres says 0.25, also interesting. We will solve it together, guys, and see what's the result. Sophia, I'm not sure what you mean by first part. You see, so the question is, what's the likelihood of winning? And you understood the game, guys. You continue throwing the die, and the die is fair until you get either 6 or 1. If you get 1, you lose. If you get 6, you win. Okay, so some person says 1-6. John, thank you. Well, we have so many varied answers. 1/6, 1/2, 1/20, 1/20. Well, you have to be careful. Is it 1/6? So, okay, we have Moishe and Ayodele saying it's 1/6. Okay, Brianna Lopez, you think it might be 1/2. Okay, thank you. I suppose, well, I mean, Grant, what about you? All right, let's see what's the solution. 5/6. Oh, 2 people. Okay, interesting. All right, so let me tell you what the solution is. The solution is 1/2. Why is it 1/2 immediately without too much effort? Okay, the die is not biased, right? Now, you see, guys, now you can say symmetry, Jomarl. Here you have your symmetry. There is no, what is that? What does it mean not to be biased? It means not to care, not to be concerned. It doesn't matter whether you get 1 or 6 for the die at the end. You see, there are only 2 possibilities. The game will not end until you get 1 or until you get 6. And since there is no preference, then by symmetry, you can say the answer is 1/2. Do you understand what I'm saying, guys? Why is a coin, why is a coin's likelihood to land heads 1/2? Because the coin does not have any preference to be heads or tails. When you say equally likely outcomes, it means that nature is indifferent. And a beautiful German word for indifference is Gleichgültigkeit. I really love it. It means like complete balance, complete lack of preference. Okay? Yes? So that's exactly what happens here. Now, let me tell you another way to solve it. Here is how you can solve it with infinite series. So suppose that you win. You win means that the last outcome was 6. Okay? How could you win? Maybe the first time you roll the die, the outcome is 6. Or maybe you roll the die twice, and the first outcome is neither 6 nor 1, because if it were 6 or 1, the game would be over, and the second outcome is 6. Are you with me? Yes? Or you play 3 rounds. If you play 3 rounds, the first 2 outcomes are neither 1 nor 6, and the last third outcome is 6. Do you understand? So that's the situation. Okay, so let me just see if you understand the general setup, right? So if so, WK means you won on the kth throw of the die. So tell me, please, what is, if you understand, what is probability of winning on the first roll? Winning on the first roll is what, do you think? 1/6. Beautiful. First roll, the outcome is, why is it 1/6? Because any of the 6 outcomes are equally likely. And when we have only one universe in which the die lands up with the number 6, and all other, and exactly 6 universes altogether. You understand? 5 universes where the die landed with another number, 1 universe with 6. Okay, so the answer is 1/6. Now, don't worry if you don't know that. I'm just trying to, you think of this as my attempt, my possibly hopeless attempt to entertain you, right? I'm trying to grab you before you lose your attention. You understand, guys? It's such an amazing thing, but you need to be patient, right? So what is probability that I win on the second round? Help me, please. What is that? And I don't need the number, just how do I calculate it? Not the same, no. No, I must not win on the first round, which means, and not lose on the first round. So there are 4/6 universes for the first round. Do you agree? 4/6 because neither universe 1 happened, nor universe 6 happened. Good. So what do we have? We have 4/6. And then on the second universe, you multiply. Now times 1/6. Now, maybe you don't know why you multiply. That's okay, guys. That's too bad. I mean, you can, if you go through the probability, then you will know why you multiply. Right? So it's this number, okay? And then in general, do you see it, guys? The third, what is probability W3? That means I win on the third round. It means I did not win or lose on the first round. I was in limbo. Same happened for second round, and on the last round I won, right? So the result is 4 divided by 6 squared times 1/6. Yes? Clear? Clear. So I just want, because obviously there are many rounds, let me calculate what happens on an arbitrary kth round. If I play k rounds, k-1 rounds, I was in limbo, neither winning nor losing. And I had a victory on the kth round. So what happened here? 4/6 times 4/6 times 4/6, 4/6 times itself, k-1 times. So it's 4/6 to the k-1 times 1/6. Yes? Yes? Yes, Grant. Why 4/6? Because that's my limbo state. 4/6 means 4 universes. I cannot have universe with outcome 1 or universe with outcome 6. So I have only 4 possible universes, namely 2, 3, 4, and 5. Because we neither won, Abraham, nor lost, precisely. So that's the 4/6 universes. While you multiply, again, If you go through my probability class, you understand. I don't have time to explain it right now. Do you hear that? Not only you are suffering. Yes. Music to my ears.
But at the first spin, it's going to be 1/6 always. Until we have lost or we didn't win, then I guess on the next round, we would put 4/6.
Say it again, Abraham. I missed it. I missed some parts.
Meaning on the first roll, the probability of winning would be 1/6. But then
Absolutely. If you win right away, there is only one possibility. You got a 6.
But then for the second roll that we do, since we didn't win or lose on the first round, it would be 4/6. And then
so on the first, so if we roll 2, better said this: if we had to roll twice, we won on the second time, right? First round we neither won nor lost, so that's 4/6. Second round we won 1/6.
4/6 times 1/6. Okay.
Exactly. Okay. Don't worry about it. I mean, if you get it, wonderful. If you don't, it's not on your exam. If that's what you worry about, right? It's a flavoring. I'm trying to make you taste what mathematics is like. Right? Especially probability, guys, because I mean, I cannot understand how people not like it. I mean, just because it's hard. It's just because your graphic card is not working. That's why you might not like it. Right? It's just like your best video game. I know you like playing video games. You're still young. And when you're getting frustrated, it's because it's not running well on your hardware, sorry, right? But that we need to update it. Yes, good. So in general, probability of winning on the kth round is 4/6 to the k-1 times 1/6. And so we get the summation. We get the summation. I wrote it in this compact form. And if you want to see what it is, it's 1/6 plus 4/6 times 1/6 plus 4/6 squared times 1/6, etc. Which I can see. You can see I can factor out 4/6 here, guys. You see it? I factor 4/6, and what I have in the parentheses is probability. So again, it's the same summation we dealt with just a moment ago. Probability equals to 1/6 plus 4/6 probability. Solving this equation, I get that 2/6 probability equals to 1/6, which implies, look at it, just cancel out, cross multiply, whatever you do, right? And you get probability equals to 1/2. Yes? Which is exactly something we can do without any calculation. You understand? Look at what the amazing part is, that we can close our eyes and not see infinity, but it's there. Here is a very popular problem in the 1950s. Let's see if you can answer it. And let's see how you answer it. Already? So you can, by the way, I have a video I translated. If you want to know who is von Neumann, I translated a video from German, but there is actually better than that. There is a better video available in English that was not available when I made the translation. I think I linked it below. Okay, it's a very good documentary on a very, very interesting person. They used to call him one of the 3 Martians. You understand? He was brilliant. There once people from, he's the father of computers. So once people from IBM came to him, they had a problem that they wanted to design a computer to solve, and they asked for Neumann what that solution might be. And for Neumann, like a machine that he was, suddenly left his body. His eyes were staring into the distance. And when he rebooted, he said, "Gentlemen, you don't need a computer. I have your solution." You understand? This person was the machine, the way he was thinking, right? He was a computer himself. So here is a problem that was asked of von Neumann as a joke, and he answered it instantly. So there is a joke about it. Let's see if you answer it. So 2 cyclists start 20 miles apart, as you see in this picture. You see? They each move towards one another at a speed of 10 miles per hour. Now, on the nose of the first cyclist, there is a fly. This fly takes off and moves at a speed of 15 miles per hour. It moves to the nose of the other rider and immediately back. So it never slows down or speeds up. It always moves back and forth at the constant speed of 15 miles an hour. Do you understand? Until and the fly will continue moving until those two cyclists will touch their noses. You see that they will touch their noses. Good. Now the question is, how much distance will the fly have covered until they touch noses? Clear? The fly goes back and forth, the cyclists are moving to each other, they kiss with their noses, trip is over. How much distance will the fly have covered? Well, interesting. So we have von Neumann followers. No? I will tell you how I solved this question. I will show you below, right? And maybe you would laugh as well. Okay, so there is an easy solution to this question and there is a hard solution to this question. He's allowed to go out since he's not registered. My cat, I mean. Well, he's not auditing, he's audible, right? All right, guys, how many people? So, okay, so we have, okay, now another person, Ayodele, thank you. So we have 15 miles possibility. We now have another solution, maybe 20 miles. Any more? I'll give you, maybe it's very unfair, but I'll give you 2 minutes, okay? I don't think it's a very good amount of time if you never heard the question before. Took me much longer to solve it. I think it took me an hour when I first heard this question. Okay, thank you, Abhishek. $300 miles, interesting. Okay, 5 miles. We have all sorts of variable. Exactly, Alexandra. Okay, right, guys. Let's see for a moment. All right, guys, let's do it together. Not a lot of time, don't be worried, it's fine. Right? Let's see how we do it. So again, very famous, and the way I solved it was very different from von Neumann solution. Maybe let me show you first the easy solution, guys. Okay, so the easy solution is the fly is moving either forwards or backwards, but always at the same speed. You agree? So the total distance traveled, it's the amount of time required for the cyclist to meet multiplied by the speed of the fly. Do you agree? Distance is velocity multiplied by time, or speed multiplied by time. Are you with me? So if I know how long the fly stayed in the air, it was always moving back and forth. You know, sometimes it covers the distance this way, sometimes backwards, but the total distance it covers, because it always travels at the same speed, will be 15 miles per hour multiplied by how many hours it stayed in the air. Do you agree? Guys, do you all see that? Now, how many hours did they stay in the air? Look at this distance. Do you see this, guys? The bicycles, when they meet, yes, exactly, 1 hour. The bicycles, when they meet, each of them covers part of the track. Even if they did not move at the same speed, look at it. If this bicycle is slow and this one is fast, do you see that? They still together swipe away the full distance, right? The distance traveled by one bicycle plus the distance traveled by the other bicycle is the distance between the cyclists. Do you see that? Very important aspect. Do you see that, guys? Right? So because they, so in particular, what I do is I take the velocity traveled by the first cyclist plus the velocity traveled by the second cyclist, multiply by t to get the time, and that would be 20 multiplied by t equals to 20. Are you with me? Why 20? Do you understand why I do that, guys? Look at it. Suppose they meet, I'm actually now, it's going to be symmetric, but suppose I did not observe symmetry, right? Let's say I don't know, maybe one is traveling at one velocity, the other one is traveling at a different velocity. So I did not observe symmetry. So how much distance was traveled by this guy? It was his velocity, let's call him V1 velocity, right? Times the duration of time it took him to cover this, right? Now this traveled at the same time velocity 2 times the same duration of time, which means that we have this, we have V1 plus V2, I just factor out the t, equals to the initial distance. Do you see that, guys, right? You need to see this, and otherwise anything here would not meet. They are moving, right? You're seeing how they swipe away the same distance. If one cyclist is slower than the other, they still together in this, as they meet, they completely swipe away or cover that full distance together. Yes, that's the invariant here. So in this case, V1 plus V2, V1 plus V2 equals to 20 miles per hour. And so what we have is the distance is also 20. So we have that what we need to do to solve for t, we need to take distance and divide by V1 plus V2. So that would be the amount of time is 20 divided by 10 plus 10, or 1 hour. As many of you can see simply without any calculation by just symmetry. Yes? You're kind of experienced with the moving, hopefully, and you understand something about velocities maybe.
So I just want to confirm I was right. Like, so it's 20 miles, 20, right?
20 miles, yes. So
Okay.
they meet after 1 hour. Do you see that, guys? They meet after exactly 1 hour. And in that 1 hour, the fly was always moving, doesn't matter back or forth, it was always moving at 15 miles per hour. So the total distance covered, as Alexander and some other people might have said, is 15 times 1 hour, or 15 miles. The fly traveled exactly 15 miles. Let me ask you this question if you understand it. How many trips, how many back and forth trips did the fly execute? Is it 1 trip, 2 trips, 3 trips? How many back and forth trips did the fly execute? You know, it lands on the nose of one guy, immediately takes off and tries to return to the previous guy. How many trips? Sophia says 1 trip. Moshe agrees. Now we are up to 2 trips. It's like a bidding contest. 2 trips going 1, 2 trips going to 1.5 trips. Well, I mean, trip is meaning you change direction, right? So it's integer. Okay, John says infinity. Okay, well, that's a big price. Interesting. You don't see it, guys? How many trips? Well, let's try to look at it. The fly is moving faster than the cyclist. Do you agree? So do you agree that it will reach the nose of the other cyclist before this cyclist will do so? Do you agree that if this is cyclist 1 and this is cyclist 2, the fly will reach cyclist 2 before they meet? So there will be one trip. Do you agree? And now the distance between them has shrunk, but if I zoom in, it's still the same picture, with just not the 20. Do you agree? The distance has shrunk, but we still have distance between them. And now the fly is on the nose of the other guy, who is also traveling slower. Do you agree that it will be able to execute a second trip? Because it's if the fly, again, forget about this picture. Now the distance between them is smaller. I zoom in to make it look like the same original situation. Do you agree? I can zoom in and make a short distance look like it's long. Can you imagine that, guys? You're not confused? Here, look at it. They move, and this guy moved a little further, this guy moved a little further, and now the fly is here. Yes? Now I can take this distance and I can expand it and make it the original picture. Not the 20 miles. You can erase this. Just make it look like the original picture. I'm just trying to show you how many trips the fly executes. Okay? Do you agree? I zoom in and now I have the same picture now, but except that the fly is now here. Now again, this fly is traveling faster than the cyclist, so it will reach the nose of the other guy before they meet. So now the interval becomes smaller, but I can zoom in and I can make it again this look like the same interval. You agree? After every trip, the fly has some distance to travel, right? After second, third, fourth, you agree? Which means that the fly will execute infinitely many back and forth passes. Can you see that? You didn't expect it, didn't you? It's obvious.
Will be a point in time when it will stop. So there will be a definite, because they will meet at some point.
That's another question, Alessandra. Your internet is a bit slower, so voice comes muffled. The procedure, we will talk about.
Sorry.
That.
Did you understand?
No trouble. Can you, maybe it's better now? Try to say it again.
So I was saying that, but there will be a point in time when the cyclists will meet. So there will be a definite number of trips that the fly will have covered.
So you're saying they're finite?
Yeah.
The number of trips. No, the number of trips, the distance the fly covers is finite, but not the number of trips. It executes infinitely many back and forth trips.
But they meet at some point, and that's when it will stop.
But each trip is shorter, right? So first trip is the longest, next trip is shorter, next is even shorter. They get shorter and shorter, but they're nonetheless back and forth trips. I'm not claiming they're the same distance trips. I'm saying that they're back and forth. How many back and forth?
Yeah, I understand. But even when they're really, really, really close, at some point they will like meet. And,
yeah, but between them, the fly will be bouncing between them. So you can imagine that they're meeting, their noses are coming closer, and you can see you can make even a funny cartoon if you have the patience. And the flies go, right? Just like a ball bouncing back and forth. Yes? So the fly will execute. It's very simple logic. How do I know infinite? Look at it, guys.
Professor,
yes?
Professor, is that similar to oscillating? Where it just
yes, there is. You can think of it as an oscillator, but again, an oscillator does not move at a constant rate. So a spring speeds up and slows down. So it's in this case, it just moves back and forth, but at a constant rate. Okay, so oscillator is a little bit more complicated than this type of thing. So if you are interested, we can also talk at some point about oscillators. Where did you all disappear? Right, here you are. Yes, at least one person is excited, huh? Grant. You should all be excited, guys. I mean, you should be hungry, right? You should be gluttonous, right? Can you imagine how many things we can talk about until you lose consciousness? So, exactly. Hungry for knowledge. Will make you a soul food, right? A hamburger with what? But Bezo functions. here we go. So here is what I'm saying. Here is this line. So they're here, and the fly is here initially, right? After they traveled, look at it. I'm not even paying attention to the distance. They traveled, right? So blah, 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 blah. Now this guy is here. Now this guy is here. The fly starting here moves faster, right? If it moves faster, it will reach the nose of the other guy before they meet. Do you agree? Flies traveling faster. It will reach the nose of the other guy faster before they meet. So this would be the picture that I see. So there would be one trip. Do you agree? Yes, their noses meet. I mean, so it seems that it would, but that's a good question, Nicole. Amazing question. We will talk about it. One of our goals is to understand the nightmares, right? Or sort of sleep patterns that we have. Do you have nightmares? I have them every night. I'll tell you some of my nightmares. So here is that fly. Now again, it moves. Look at it. You see this distance? It will reach the nose of the other guy before they meet, right? So now the picture is kind of like this, and the fly is here. Again, it will reach the nose of the other guy before they meet. You see, because this distance will be traveled always faster by the fly. Do you agree? They traveling slower than the fly. So the distance that is between them will be traveled faster by the fly. So the fly will reach the nose of the other guy before they meet. Is it clear? And you can see that it will continue forever.
Professor.
Yes.
At some point, do the cyclists meet?
Well, but that's an amazing question, Nicole.
I'm really confused because if they meet,
you don't even understand how good of a question it is, and we describe that. We're going to talk about more paradoxes. We will talk about this, and then there is going to be a bunch of limits, and then again we will talk about limits and infinity and how they are related, and do they even meet? But perhaps think about it. I mean, you see such situation. You've seen cyclists move towards one another. Your intuition tells you that they do meet. Whether they actually meet or not, that's now a much more sophisticated question. What is actual here? But your empirical ideas, your empirical impression tells you that they do. Right? I mean, if you go and try to walk towards your friend, I mean, I'm supposing that you will meet, right? And the fact that the fly is doing something in between should not affect it. Of course, that now you can go deeper into it. The theory of relativity is about it, right? Is time affected by how you move or what you're doing?
Yeah, the person wrote a comment, which is what I'm asking. Like, if they meet eventually, the fly has no distance to go back and forth between.
Well, but you see, before they meet, as they're meeting, the fly is moving back and forth. So you see here, they're meeting, the fly goes back and forth.
So we're not claiming that they meet?
We are. I am claiming at the moment that they are, but wait with your very interesting comment. Why not? Look at it. The noses are touching, right? The fly goes, you see, what bothers you, you don't believe that the fly executes infinitely many passes. But what's the problem? It doesn't have to execute this. It doesn't have to travel the same distance. The distances it travels back and forth are shorter and shorter, as you see in this picture.
Mm-hmm.
Yes, it's not the same distance it travels. So, but we will talk about your objections. It's a very interesting objection, and I will see in another paradox soon enough whether or not they meet or not. Okay. Hopefully, we'll get there by. Well, they can get within any distance. The distance between them can be a micrometer, okay? So those cyclists are actually points, right? And the fly is a point between them, okay? So they can arbitrarily get within any distance to one another. Okay, good, let's continue. So here, using this idea, I'm just going to sketch how I solve this problem. Okay, guys, I'm not going to bother explaining it too much. I want to move on. But here is how I solve this problem. Okay, so that's initially, my initial solution was pretty much like this. So I said, let tk be the time it takes the fly to execute the kf trip. In other words, first trip, it's t1, second trip is t2. I right away observe there will be infinitely many trips, as I just tried to explain to you, right? And the distance that it will, that there is also a distance, I call it dk minus 1. Initially distance is d0. That's the distance before we press play and the motion begins, okay? And then once the fly landed on the nose of the other guy, it notes how much distance is between the cyclists. So dk minus 1 is the distance after the k minus 1 trip between the two cyclists. You understand? So the fly landed on the nose, and now of course the two cyclists move together, so it sees how far it has to fly. It will fly less because the cyclist will come closer, but I mean, it sees what distance is right now between the two cyclists. Good. And then using this information, I set up a recursive equation. I say I have to do it in symbols, otherwise it's a bit complicated. I mean, I do not want to ahead of time to know what's the distance. I know d0 is 20, but I do not know what's d1, d2, d3. I don't want to calculate them separately. I don't really care about those separate distances. So what I say is the distance traveled, the distance that remains between the cyclists, right? Between the cyclists after the k minus 1 trip is a distance that will be covered. The distance will be covered if I add the distance traveled by the fly plus the distance that is traveled by the guy coming towards the fly. You understand? It's the same situation as with the two cyclists coming. I mean, the distance covered by the fly plus the distance covered by the other cyclist will be the total distance that I'm seeing. So I'm seeing this pattern. And then I see another thing. I see that the distance that actually will be traveled, this is the next distance that I will see. It's the distance that I had before minus the distance in this amount of time removed by both cyclists. Okay, don't worry. I mean, if I am assuming that maybe one person understands me at the moment. Okay, maybe less. Okay, maybe nobody does. So this is the formula that I come up with, and I solve for time, and I solve for distance, and look what happens. Here is my formula for the distance. I get an infinite sum. At the end of this infinite sum, what do? I have the calculation and I get 15. Same thing that we did before, right? I calculated it using infinite sums. And this is the clever solution we already discussed, right? So you already understood that you can avoid this infinity. You can ignore it in some sense, even though it's there. It's there in this problem. You can ignore it and still get the right answer. And this is what happened to von Neumann. Von Neumann in 1 second solved it the way I showed, more or less. I'm not sure what symbols, maybe no symbols. He just kind of calculated it right away. So the person that asked him was so amazed that he solved it so quickly. Wow, you figured out the trick. And he replied, what trick? I summed the geometric series. It just pretty much just right away just crunched this infinity and solved it. Didn't really bother thinking about it. All right, are you ready, guys? So let's move to the next challenge. Okay, guys? And this reminds me, I always mention it since 2018 when that really happened. So my brother used to, at some point, come to school and recorded some of the lectures that I had. He didn't care at all about the math, only just made fun of the way I speak, right? With where I place emphasis or my English or anything else that he could find funny. And then one day he tells me, I'm actually interested in infinity. Will you help me? And I thought, sure, that's amazing. I'm going to help him with infinity. In the morning, he wakes me up and drives upstate, 2-hour drive, parks the car, and we exit, and it's infinity IQ 30. He bought a bargain for $200. He brought a 1997 or 96 car, from the infinity sequence, right? And what he wanted my help for is to drive one of the cars back, of course, right? And for this car, another thing that he did for this car, he bought the antenna. He bought an antenna. Let me show you what sort of antenna that was. You ready, guys? He bought this antenna. Let me show you the picture. You see this picture? Here, you see it, guys? you have this type of thing in your cell phone or something or some variant of that. That is helping your cell phone receive and transmit signals. You understand? You have this type of device. What my brother bought actually was the triangle version of it. Let me see if I can, where is it? Fractal antenna. He bought one that, it's funny, I saw it just a moment ago. You see in cell phone, you see this, guys? This is the cell phone thing. This is how it looks like. You see it? Yes? And he brought a variant of it that is, I think, it looks like this. It's about $30 or maybe $60 at the time. To attach to his Infinity car, he bought this antenna. Now, we will not go in this class and understand we are too, too primitive for that at the moment. We will not try to understand why such antenna is good for receiving and sending signals, but we will learn how to manufacture it and become rich along the way. Are you ready? So here is the manufacturing process. So what you have to do is get yourself a metal sheet, a square metal sheet 1 by 1. Okay, measurements are 1 by 1. Good. You subdivide each length by 3, creating how many squares? Creating 9 squares. Do you see? 3 by 3 is 9 sub-squares. Good. If the area of the square is 1, we just normalize it, 1 square. What's the area of each of those subsectors? Help me. What's the area? One over 9. So just 1 over 9. Look at it. It's 1/3 times 1/3, right? There are 9 of them. They're identical, so it's simply 1 over 9. You see how you can do it? It's all of them. They add up to this full thing. There are 3, 3, and 3. So area is 1 over 9. So what you do is you puncture one out. You puncture this one out. That creates this one hole. You've seen it in the picture, right? So here it is. You see it? Where is it? Here. That's the middle hole. You see? I created the middle hole. Good. That's here. So how much material did I remove? I removed 1/9. You agree? Then from each of the remaining sectors, they look like the original square. Do you agree? They're just much smaller, but look like the original square. I will subdivide them into 9 parts and remove the middle. Okay. What's the area of this square? Could you help me? What's the area of that small square? Yes, or 1 over 9 squared, guys, right? So it's not always, the numbers are not as nice as what they might help us with. So we need the pattern, right? And look at it, because I have 8 such squares, I remove 8 over 9 squared. You agree? 8 over 9 squared. Do you see why it's why is it 1 over 9 squared? Because it's 1/9 of a 1/9. It's 1/9 of a square that is itself 1/9. 1/9 of a 1/9 is 1 over 81. Or 1 over 9 squares. Are you with me? 1 over 9 squares, and there are 8 of them. And so how much did we remove, guys? Are you with me? We removed here 1 over 9. In the second step, we removed 8 over 9 squared. Do you agree? And here, how many very, very small squares did we remove? And what's the area? What's the area of this really, really tiny square? Exactly. 1 over 9 cubed. Guys, you understand how we know that easily? Look at it. Do you understand how I figured that this square is 1/9? It's because there are 9 of them, right? And this square is 1/9. 9 of those squares make a 9th, right? So how many of those squares make the full thing? 9 squared of those squares make the whole thing. So it's 1 over 9 squares. And this one is 1 over 9 cubed. They're always the middle. So how many do I remove here? I remove here 9 cubed. All of the tiny ones are 9 cubed. Now how many of them? Look at it. So it's 8 here, and 8 here, and 8 here, and 8 here, and 8 here, right? So how many of them do I remove? You don't need to count them. You can see it. It's not 48. No, look at it. 1, here it's 8. Now each of those will contribute 8. So we have 8 boxes here. You see, we have 8 boxes surrounding, and each of them contributes 8. So how many in total? 64. You see 64? Because each of those boxes will contribute 8. And we have 8 such boxes. So it's 8 times 8. 8, 8, 8, 8, 8 times 8. So it's 8 squared. Good? And if I could, and of course, then you look at those, they become very tiny. You continue doing that forever. You understand? You do it further and further and further. It's not over, this process. So the next layer is 8 cubed over 9 to the 4, and so on. Clear? Now the material, it's metal. Once you punctured it out, you can melt it and make another square sheet. You agree? You can recycle the metal that you removed. Now the question is, how much material did you recycle? You see, 1 over 9 is what you removed. It's recyclable. How much did you recycle? Precisely. How much did you recycle, guys? Very simple calculation. You see what we're getting? We're getting again that infinite sum. Okay, wonderful. So all of you, or I'm hoping, Elazar, what do you mean? What is this zero infinity? Well, infinity, maybe. Look, this is how much we recycled. Let's look at it together. Look at it, guys. So here is the summation. You agree? This is the summation. I hope you understood how I obtained it. Now I already know how to solve it. I just put parentheses around all the terms after 1 over 9. Put parentheses here. And all I need to factor to make it look like the original sum is 8 over 9. Do you agree? So you see what I do it, guys. Look at it. You see that I will place parentheses here. And then I see that what I have in the parentheses looks like the original sum. Exactly the same. Except for the fact that it starts later. So I need to factor out 8 over 9 to make it start at 1 over 9. So that's what I do here. Look at it. 8 over 9 will be 8 over 9 squared here, right? 8, 9 times this will be this term. You agree? So I have area equal to 1 over 9 plus 8 over 9 area. Yes? And what do I get? If I solve this equation, I get that 1 over 9, look at it, 1 over 9a is equal to 1 over 9, which means a is equal to 1. You understand what I'm getting, guys? If you calculate it like we did before, this equals to 1. Yes? Now interpret this result, guys. What does the 1 mean? I hope you understood how to carry this calculation, but what does the 1 mean? We recycled, Alexandra, exactly. We recycled everything. Which means, look at what you have to do, guys. Just get yourself one metal sheet, puncture it out, create the antenna. You can sell it for $60 or something, and then just fuse the metal again, and you can manufacture another one, and you can do it forever. You understand? So here I gave you a perpetual means of constructing material, or constructing antennas out of nothing. And it's used in your cell phones, you see? Well, you need to, the manufacturing process requires puncturing out of metal, right? Right, because you need to see that you're you're building it up. Why go through the whole process? I mean, you're just arranging air to be in this pattern so you can see it in the antenna. Why go through the process so you can sell it? Production. Sophia, can you do this with other numbers, or is just number that are perfect squares? You mean puncturing? You can make many things like that. I mean, those patterns appear in mathematics very frequently. This pattern or other, right? It doesn't have to be this particular pattern for the antenna. Many other patterns can work. This one is just very nicely regular, okay? So let's look at, I'll show you some more patterns like this, okay, guys? So let's now go back to limits. Take a deep breath. I mean, right, it was a sort of flavor. I mean, I'm hoping you understood everything I said. You can reread the notes, but it's not as of yet a requirement. It's a sort of attempt to keep you engaged and see that there is so much more that comes, right? It's just, here we have just the very, very basic ideas, and still we're already able to see something interesting. Without classes, what is that, Elazar? That's what my brother was doing instead of, he was smoking weed while filming my lectures, for instance, right? This bastard. It smelled of him, you know, I mean, of weed specifically. Right, in the class, and very, very strongly. Yeah, so let's go back to limits. Yes, I see. Thank you, Elazar, right? Here is limit as x goes to a of f of x. Would you please remind me what's the idea? What do you do when you see limit? What do you do to f of x? What do you do to f? When you see x is approaching a, what is your instinct? What do you do? You see, I'm giving you a hint. What do you do? Oh, some of you say f of a. No, you don't do f of a. What do you do? What do you, when you see a limit, what do you do? You plug values very close to a, but never a. You understand, guys? It's very different concept. You plug all the values that are closer and closer to a, but never actually a. Okay? Very good. Plug near a. Very good idea to remember. Plug near a. The limit as x goes to a will be, of x will be a, but not the limit of the function. I mean, the function is the process. You understand? I feed. It's this question. If I feed you something similar to the actual product, will you be healthy, right? If I feed you artificial apples, you see, that's what happened to people. I mean, they react, let's say, to those very, very, how do you say, progressive people. You know, they go to a store and they buy organic food. Why do they buy organic food? Because organic to them sounds very nice. Organic, it's real. What you think food is not organic, right? I mean, what is it, made of silicon or something, right? So they are very, let me not say what they are. And then, of course, why do people go and buy bread which is gluten-free? Because gluten-free means they're not gluttons. That's pretty much why. Right? If you buy food with that is not gluten-free, then you're a glutton. That's pretty much, it works on that silly psychology level. Good? But why did I remember of that thing is because, look at it. You are just now saying that, that you think that the result on your health, on your f of x is your digestive system. You just said that the result on your health is the same if I actually eat the real thing or if I eat imitation. You understand? If I eat a fake apple, you're telling me it's the same result as if you eat are real apples. So then I wonder how many of you buy organic foods. Do you understand my logic? Or you completely lost me? You think this person is right? But you understand, plugging something that is not A might cause the function to digest it very differently. The limit is not known. Understood? No. The function f of x, right? So what is f of x? F of x is this person, he sits around and he digests, right? So you feed him something in, you feed him a fake A, and this is the function, this is f. Then digestion is working through, and what comes out is something you call f of x, f of A, I'm sorry, right? What comes out is f when you processed this fake A. Now, what comes out if he eats an actual A might be very different. That's what I'm saying. Understood?
But if A hat is very similar to A, how is it going to be very different than?
Well, exactly, because you just see mathematically that it can be. You see, so I mean, your questions indicate to me that you should not be buying, organic foods, because what does it matter? Imitation, fake food, or real food seems to be the same for you.
No, I don't buy organic food.
Well, good for you. Right? They're wonderful, right? You understand?
Yeah.
Good. Let's move on. It's very simple, guys, right? The question is if you eat imitation, will it be digested differently, even if the imitation is very good? If the answer is essentially they are digested the same way, then the function is continuous at that point. If the answer is that the digestion is very different, then the function is not continuous at that point. The limits are very different from actual thing. You understand? The imitation and actual thing, there is a difference between them, which means it can affect the digestive process. Yes? Let's move on. Now let's talk about what it means to take limit as x goes to infinity. That's the main goal of this chapter, finally. So x goes to infinity, what do we plug into the function? Could you tell me, actually, what do I plug into the function? Of course, I think in analogies. What do I plug in the function if I take limit to infinity? Wonderful, Erin. Right, very good. I plug big numbers, big numbers. Don't you see that, guys? Big numbers. God damn it. So, and if I take limit to minus infinity, I plug big numbers with very negative sign. I am not okay since a while. Thank you for asking, right? I mean, I've been not okay since I started teaching, and probably way before, right? We can trace the problems that I had to my childhood. I actually studied psychology initially, right? But then I realized it's meaningless, right? It's not capable of solving my problems. So help me calculate this limit. Let's see if you can do it before I explain. Limit as x goes to infinity of x squared minus 1 over x squared plus 1. Oh my God, Elazar! Now you ask me. You see, so they were doing tests on me, and apparently I don't cast shadows, right? And they tried to find my pulse, and apparently they cannot figure out where it is, where it has gone. No heartbeat and no sleep. This thing tried to record if I sleep, and it says no information, no measurements. And in fact, if you search for my name, and you can do that, you will see that I died in 1983. It's absolutely true. That died in 1983, I don't know. Different people die at different times. So the answer, it is 1. Yes, guys? The limit here is 1. You got it? Now, how did you get 1? So some students, beginner students, reason this way, guys. So they say, well, some of them do it, right? Infinity squared minus 1. Well, infinity squared is infinity, minus 1 is infinity. And infinity squared plus 1 is infinity. Now, a number divided by itself is 1. Do you agree with this reasoning? Do you agree with this reasoning? No, this reasoning, that's you should have seen this, beginner students. That should have given you a psychological priming into thinking that I do not. So here is the situation, guys. Here is the problem with this reasoning. First of all, this symbol does not mean a number. It means just that there is growth without bound. And when you say it's growing without bound and it's growing without bound, you forget to mention what speed. Okay? It's a very crude symbol to indicate maybe the numerator grows very rapidly compared to the denominator, or vice versa. You understand? So infinity over infinity is not a number divided by itself. It's just that there is a tendency to grow in the numerator and there is a tendency to grow in the denominator. They are fighting against one another. And how it's resolved, we need to determine by a different strategy. It's not a real infinity, but it's also not a number. So when you say something divided by something is 1, you usually mean a number divided by itself where the number isn't 0. And of course, guys, you want to understand, do you understand why something divided by itself is 1? Or you just memorized it? So here is what we have. Look at it. I take limit as x goes to infinity of x squared minus 1 over x squared plus 1. And what I do, I factor it out. I factor it out. Factor x squared out. The biggest power I factor out. You think because there is a 1 I cannot do it, but certainly I can. Look at it. X squared times 1 is x squared times 1 over x squared. It's 1, right? You see it? Yes? See the same thing in the denominator? And x squared over x squared, it's the same number over itself, and the number is positive, right? Because I'm going to plus infinity. Of course, I can assume the number is large and therefore bigger than 0. So I can cross it out, and I'm left with limit as x goes to infinity of 1 minus 1 over x squared over 1 plus 1 over x squared. Yes? And look what happens, guys. And we take the limit to infinity. This part is now very easy to judge. 1 minus this number is 1 divided by a huge number, which becomes 0. 1 plus 1 over a huge number, that this part also becomes 0. So it's really, now it's clear that the answer is 1. Yes? It's clear that the answer is 1. And now we make, at this stage, we make a definition, guys. Let's see if you use this word, but maybe you never thought about what asymptotes are. What asymptotes are. So if we have that limit as x goes to infinity equals to some number L, we say that the line y equals L is a horizontal asymptote. And what are asymptotes? Does anybody remember what are asymptotes? Would anybody like to say before I explain what they are? Why? So if I say the word asymptote, have I made anyone, impressed? I mean, did I say anything reasonable? What is an asymptote? What's the idea of an asymptote? Why would anybody give a damn? Well, so Sophia says a line, but doesn't meet at a certain point. I mean, who cares if a line meets or doesn't meet? No, an asymptote, guys, is something entirely different. Okay. So let me tell you what is an asymptote. So think of asymptotes as familiar shapes, right? So we have this graph, and this graph is, I presume for many of you, you don't know what it looks like. It's not familiar, right? If I were to draw it, the graph will not be familiar. The graph, by the way, is, the graph of this function is x comma x squared minus 1 over x squared plus 1. That's the graph. It's the collection of those points. If I plot them in the xy plane, the shape might not be very familiar. You agree? But if x is very large, what I will get is that the y coordinate is essentially 1. So essentially, if x is very large, this is essentially x comma 1. And that's a much more familiar shape. X comma 1, and you try to think, what sort of shape is this? And that shape, and I will show you in a moment, I will show you an animation of it so that you can actually see what shape it is, okay? What shape is this? Somebody says it's a circle. No, it's not a circle. Okay, let's clear it for a moment. And for a moment, just let's pause and explain exactly, Alexander, it's a line. Okay, guys? Now think of what asymptotes are doing. When you say to a girl, your eyes shine like two moons, right? You want to impress a girl and you quote poetry, right? And why is she impressed by poetry? And trust me, not all of them, but some of them are very impressed by poetry, right? And you see, what you actually do, you make her understand what her eyes are like. You understand? She doesn't really understand what her eyes are like, but she saw the moon. And so she knows that there is one moon here and one moon here. Now she understood it and she likes you for that explanation. When you look at a cloud and you say it looks like a fluffy sheep, now a person can imagine what the cloud looks like because they've seen sheep, right? Or unicorns or whatever else you like. So an asymptote is a familiar shape, a simpler shape, a comfort shape. Clear? And so the question for this graph, let me show you what happens to this graph if I plot it. Okay, let's actually do that here. Here we have it, guys. Are you ready? Here is that graph. Look at it. This is the graph somewhere in the picture. You see, looks, well, doesn't look too familiar, right? Let me lift it up a little bit and let me scroll the graph to the right. Do you see this curve? Tell me what's happening to that curve. I scroll to the right. Look at it. I'm now at 4.4, 4.5. What's happening to that curve? Look at it. Do you see it? Look, oh, wow. What's cutting to it? The curve looks like a flat line. It looks constant. It's not really constant, guys. You see, it's a little below 1. The limit is 1. That means plug in very large numbers and you essentially will see a horizontal line. Yes? You see a horizontal line? Look at it, because the graph, what you're seeing here is the graph of x squared minus 1 over x squared plus 1. And this graph, look at it, the number that you see here is essentially 1. Do you agree? If x is very large, the number is essentially 1. So that number is, so the graph is essentially x comma 1. Look at it, you see? It means any x, altitude is 1. What shape are we tracing? Any x, altitude is 1, we're tracing a horizontal line. Do you see that? So when you say a horizontal asymptote, you're just saying that the asymptote is just whatever Greek or Latin word, doesn't matter to you, right? But the idea of what you're saying is, doesn't matter crossing or not crossing. What matters is that the shape of the graph looks like a horizontal line. And a horizontal line is, it's like this original graph is your cloud. And this cloud looks like a straight horizontal line. That's all you're trying to say. Clear? Now, guess what other thing has that straight horizontal line? Have you ever seen a picture of an AKG? Right? Is it ECG or AKG? You know, like you monitor the heart. You go beep, 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 beep. Can you tell me what is the horizontal asymptote of my AKG? Exactly. It's 0 because I have no pulse. Understand? If you have no pulse, it's a straight line, right? But when I was alive, I had a pulse and then it flattened. Okay, that's the horizontal asymptote of my graph. Understood? All right, let's finish with the next problem and you'll help me. Exactly, because I died in 1983, precisely. So my AKG shows a horizontal asymptote. It's not a perfect horizontal line, you know, but you scrolled far enough into the future, far enough to infinity for this graph to be a horizontal asymptote. In other words, very difficult to distinguish from a straight line. Cause of death, annoying students. They killed me in an alley. So here is I can tell you many stories about students and where they live and how close to me. So here is the next question. Find horizontal asymptotes for the function f of x equal to 2x cubed plus x minus 1 over x cubed plus x squared plus 5. Go ahead, calculate. Go ahead, calculate, guys. Yes, Elazar, were they arrested? Well, they were arrested in their development. Oh, by the way, guys, if you have any energy afterwards, we will solve problems, right? I mean, you were not volunteering problems, so I guess I will volunteer problems upon you. Okay, Abraham, very nice. The answer is correct, Sarah. I will scroll it down, okay? Here is that function. It's 2x cubed plus x minus 1 over x cubed plus x squared plus 5. Okay, the answer is 2. Let me quickly, before you have to go, guys, let's do it together. You see it? I will look at the numerator and factor the biggest power of x I can find. In the numerator, the biggest power of x I can find is x cubed, okay? So factoring x cubed, look what happens here, guys. Here we need 2, here we need, it was originally x, I divide by x cubed so that when I multiply x cubed through, it simplifies. So it's x over x cubed minus 1 over x cubed. Good? And same thing we do for the denominator. We factor out the biggest power we can find, which is x cubed. Look at it, I factor it out and I can cross away the x cubes. You agree? I can cross them away since they are, well, they are numbers, big numbers. So what I'm left with is 2 plus 1 over x squared minus 1 over x cubed, and similar thing on the denominator. Do you see that? Now, each of those parts, they go to 0. 1 over x squared, it's 1 divided by a huge number. It goes to 0. This goes to 0, and the result is 2. Now, what does the 2 mean, guys? The 2 means that the graph is essentially, the altitude is essentially 2. Like I showed you in the previous picture, if I graph this thing, I will see a horizontal line if I scroll to the right. You see, x going to infinity means scroll the screen to the right like I did for the previous question. You see? Here is the previous question. I scrolled the screen to the right. You see it? Here was the original picture. And I scrolled it to the right and I began seeing a flat horizontal line. Essentially, I cannot distinguish it from a flat horizontal line. So For this, for the previous problem, the horizontal line is at y equal to 1. You see, y equal to 1 is representing it. Next, for the second problem, we solved that the limit is 2. That means the horizontal line will be at y equal to. Clear? We can do many of them, Sophia, right? We will do plenty of questions. And we will try possibly to graph them. Maybe I actually will graph it here. So let's look at this limit. It's 2x cubed. Plus x, am I right? Or minus x, I forget so quickly. Plus x minus 1. And the bottom is x cubed plus x squared. Plus 5, yes? Now let's look at this graph, guys. Here is that graph. Look at it, there is some breakage point, and what did we do? Look, the graph looks pretty complicated, but let's see what happens if I scroll to the right. You see? What's happening as I scroll to the right? It becomes 2. If you push limit as x goes to minus infinity, all you are doing is you are scrolling to the left. And you have, again, the horizontal asymptote is y equals to 2. Do you see that? That's 2. It's just the altitude. It's just the y coordinate. The y coordinate is just 2. So that's what the horizontal asymptote is representing. It looks like a straight line. Clear? Wonderful, guys. So let me let you go in case you want to go. So 2 things we do, guys. You let me know in the comments if you want a round of what, when, where, or maybe today you're tired and you want to do right away problems, right? So write in the comments if you want a what, when, where. If you want to go, then goodbye. We're going to solve a few problems together from the textbook. And I'm stopping the recording. Yes, hungry, Elazar. You're not hungry for the right thing. Okay, I'm stopping the recording.